Thank you. Thank you all for coming. I really appreciate people coming on Sunday to university, to lectures. So I wanted to tell you about gravitational waves. These are a prediction of Einstein's theory of relativity, something that we are celebrating the 100th anniversary this year, but also how to measure them and what we can learn from these gravitational waves, as we call them, astrophysical messengers. So the plan I have for the lectures are first to talk about Einstein gravity. I know you've been hearing about these, and perhaps you heard everything I'm going to say, but I can't resist. I mean, that's what we are all here, and we all have different ways of visualizing these, and we like talking about it. Then I'll talk about the sources of gravitational wave, what kind of stars and astrophysical systems produce gravitational waves, and then how to detect them, which is the difficult part. That's going to be the hardest part. And then how we want to do what we call multi-messenger astronomy with these gravitational waves. So let's start then with the first part, Einstein's gravity. I know that you are perhaps experts at this already after this World Science Festival with so many events on gravity. But let me tell you a bit more about that. First, what you learned in school, Newton's gravity. You probably thought that this was canonical. It was, it was the standard theory of gravity. We learned it as perhaps a bit boring class, but it was revolutionary at his time. Newton's theory was actually a revolution in unifying theories. He had this one theory to explain how the forces between masses could predict not only how the apple falls to the earth and how objects move around in billiard balls and objects that we see every day, but the same theory could explain how the earth went around the sun, how the moon went around the earth, and the motion of all the planets that were seen at the time. That was the first unified theory. Then came Maxwell, and now we're still looking for more and more unified theories. But that was the first one. That was revolutionary. And his formula was actually very simple. It said that the force between two masses is proportional to the product of the two masses and inversely proportional to the square of the distance. So it explains everything that, every motion that people knew about the time. Of course, there is a lot more to physics than motion, but that was the theory we had. Einstein came along, and for different reasons, he came up with this theory of general relativity, which is very, very different than Newton's theory. It's not a formula that tells you about the force between two masses. In fact, he says that there is no such force. And the reason, one of the reasons he was looking for this is that in his theory of special relativity, he had postulated this universal speed limit. The speed of light was the maximum speed that any object could have. And Newton was saying that if you had two masses, the force between those two masses was instantaneous. If one mass moved, the other one would know immediately. And that violated his speed limit. So that was one of the reasons why he was looking for this theory. And this beautiful theory says that what you have is not forces between masses, but masses living in a dynamical space-time. And the masses move and change that space-time. And the masses can tell how the space-time is changing and then follow what seems like the shortest path. So Einstein's vision, and let me play this nice movie again, is that if you have a mass, it doesn't feel the force of the other mass. What it feels is the stretching and squeezing of the space-time around it. And then if you have another mass, it will go around it, just like Newton's theory predicted, but not because there is an instantaneous force, but because it's following the shortest path as seen by the grid of the space-time. So it was revolutionary, again, in a different way. So essentially what the theory says is that when the masses move, they change the space-time, they wrinkle the space-time fabric, and then that is what makes other masses move, and that happens at a finite speed. That happens at the speed of light. So now there is no more violation of the speed limit. Now the math is complicated, and I'm only going to put this formula here, but not go into the math details. There are actually very, very thick books that tell you how to do this. But essentially what he did was to put the description of the geometry of space-time in something that we call the Einstein tensor. So it's a 4x4 matrix, 4 because it has the 3 space dimensions plus time dimension, but all mixed up. Space-time is all the same. So this tensor describes space-time, the geometry of space-time, and this tensor on the other side describes the mass and energy that is in the space-time. So this is how mass determines geometry and how geometry determines how the masses move. Now, the problem with this theory, and he realized this very early on, is that the constants in here are Newton's constant, talking about gravity, and the speed of light, that is the constant in the theory of relativity. And what this says is that masses, usual masses, produce distortions of geometry that are very, 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 very small. So it does explain, after a lot of math, you can explain same things that Newton did, like how the apple falls and how the Earth moves around the sun. Those are not small effects, but those are very small effects in the curvature of space-time. The curvature of space-time is mostly flat, except near very, very strong masses or masses moving very, very fast. Now, Einstein, after writing his theory, was looking for predictions that could be measured to see whether I don't think he doubted his theory was right, but he wanted to prove to others that his theory was right. So there were some predictions that actually people realized from the beginning, and some he liked and some he didn't. One of the predictions was that the universe expands. This, when you put a spherical symmetry in this if you put some dust with spherical symmetry, it tells you that the universe is not static. In fact, it tells you that because mass is only attractive, it is compressing, but it could have started expanding and then compressing. In any case, it was not a static universe. And he didn't like that. In fact, he added a constant to this tensor in here to make the universe static, to make it stop moving. He didn't like this expansion theory. But then we realized, well, I wasn't there at the time, but observers measured that the universe was actually expanding. All the galaxies were getting farther away from our galaxy. So he took that constant away and said that that had been his biggest blunder. And now we think that we have to put it back with a different sign and with a very, very small value, but that's another story. So the story of the universe, starting with a Big Bang and expanding, is a prediction of this theory. It also predicts that there are black holes. In fact, the first exact solution to Einstein's equations was not done by Einstein. It was done by Schwarzschild during the war. He was in the trenches doing the math on a small notebook. And he realized that if you have a star, a spherical star, and you want to solve the equations for space-time, you find that there is a singularity at the center. And that singularity was what was called black hole. And Einstein didn't like it. Many people didn't like it. But now we believe that black holes exist, and that's one of the things that we hope to measure distortions in space-time from, as I will tell you later. The one prediction that he really liked, and was the one that made everybody believe in the theory at the time, and his theory appeared in the first page of the New York Times, was that light bends when it goes through a big mass, like the sun. So if you see a star when the sun is close, then you would see it at a different place than if the sun is not there. And that you could test with an eclipse. And that's what was done in in 1919, and that is what appeared in the first page of the New York Times and made Einstein very, very famous. Another prediction that's actually very interesting and very, very practical is that clocks run at different rates at different heights. So if you are at the top of a mountain or at the bottom or near the surface of the Earth, and you have an atomic clock with you, which is the most precise clock you can have, it will have different rates. You can't have synchronized clocks if you are in different gravitational fields. And that is very important, not only because it's, well, it's a prediction and a test of general relativity, it's something you have to take into account if you use clocks to measure distances. And you probably are all relying on your GPS to get here, to get to many places. GPS would not work if we didn't apply the corrections needed because of this asynchronism of clocks at different distances from the Earth. General relativity is weak. It has weak predictions, but some of those are very, very important, at least for people who get lost even with GPS like I do. So go back to Einstein gravity. The one prediction that I like the best, and the one I want to tell you about, is gravitational waves. This is a very different prediction than Newton's theory. If you have two stars or two objects like the sun and the Earth, Newton says that there's going to be circular motion around the center of mass, and that's going to go on forever. Einstein says that the two objects, the two stars, are going around each other because they disturb the space-time and they follow these geodesics. But in moving, they also produce these other distortions of space-time that travel away from the system. And they carry energy away. And if they carry energy away, then the binary system has less energy, and that means that the stars get closer and closer together. That is very, very different than Newton's theory. And it's all about these gravitational waves carrying energy away. Now, it took about 40 years or 50 years to realize that gravitational waves could actually carry energy. Most people, even Einstein, thought that gravitational waves might be, well, perhaps you chose a coordinate system that makes it look like a wave, but you can make it go away if you choose some other coordinate system. The physics is all the same, independent of the coordinate system that you choose, so perhaps gravitational waves are just a mathematical artifact. But they are not. They do carry energy away. And that's why they can be measured. And we know that is true because that effect has been measured. And I'll tell you more about that. So that's Einstein, my version of Einstein's theory. It does predict, it has many predictions because of this dynamical interaction of matter with space-time. And what I'm going to tell you first is what kind of matter produces these gravitational waves, and then I'm going to tell you how we can detect those disturbances of space-time. Sources of gravitational waves are, according to the theory, any matter, any non-spherical matter that is accelerated. So in principle, I am producing gravitational waves moving my arms in here. I'm not spherical. I don't want to be, but and in moving, I am accelerating. I'm not moving at a constant velocity in any reference system, so I am producing gravitational waves. It turns out that if you take quantum theory into account, I may not be moving fast enough to produce a quanta of gravity. So perhaps I'm not moving space-time, but according to the classical theory of gravity, anything that moves produces gravitational waves. But what Einstein realized in the very beginning, independent of whether gravitational waves were real or not, is that most ordinary mass produces disturbances that are tiny, tiny as of unmeasurable, he thought. So what we have realized since then is that if you think about astrophysical sources where you have very compact objects or very cataclysmic events, then those big masses in small radii moving at large velocities can produce detectable gravitational waves. And those are the sources I'm going to tell you about. First one, let me not skip one, is the early universe itself. In the early universe, at the very, very beginning, there was matter in the universe. The same amount of matter that we have now. Matter and energy has been constant. But it wasn't completely homogeneous. It had quantum fluctuations in there. And those are the ones that much later on produced our galaxies and the clumping of matter that we see now. But in the expansion of the universe, those fluctuations of matter produced gravitational waves because they were moving. They were changing the space-time that was itself getting expanding since the Big Bang. So we want to see those early gravitational waves. It's like a rumble. It's the same kind of rumble that we call cosmic microwave background, except that that rumble is the electromagnetic rumble that was produced by those photons getting free in the early universe and traveling to us, and they were so stretched that they are now microwaves. There is a similar kind of rumble produced much earlier. This is the microwave background produced later in the universe. Much earlier, there were these quantum fluctuations that produced this gravitational rumble that we want to detect. Now, there are several ways of trying to detect this. The one that's most promising is the one looking at the imprint of these gravitational waves on this microwave background. And you might have heard about BICEP2 news in the last year or so. They had evidence of strong fluctuations in the polarization of the microwave background that was thought to be originated in these gravitational waves. It turns out that it's not easy to see whether it's dust would produce dust in the wave from this early universe to us would produce these changes in polarization or the gravitational wave background. But there are many experiments trying to do this. They are getting more and more precise with time, so that's going to be coming soon. So that's one kind of gravitational wave produced in the early universe, like a rumble. There are other, you probably know that stars often explode. Well, not that often. It happens about once every 100 years in our galaxy. But they explode in supernova. There are different kinds of supernova. Some of these supernova are caused by a core collapse of the mass. So the stars have nuclear fuel that is producing all the light, all the electromagnetic light that we see from the stars. But then they also have mass that's compressing the stars. So sometimes the nuclear explosions balance the pressure to get compressed. But then as they lose the fuel, then the gravity begins to win until it core collapses. The core collapses into a very, very compact star, and that bounces back and produces these beautiful images that we have in the electromagnetic spectrum. But at the very center, there is a very compact star left. And that can either be a neutron star, which is made of elementary, not atoms, but the elementary particles in atoms. That's why we call it neutron star. And we know very little about how that behaves in there. But that's the most compact kind of stars that we have. It's like having the mass of the sun compressed in a radius of about the size of Manhattan. Imagine Manhattan having the mass of the sun. That is what a neutron star would be. That's how compact it is. But sometimes, if there is enough mass and there is enough compression, something else happens. There's a black hole happening. So if there is too much compression in there, instead of a neutron star, we get a black hole. So this is how we know how many neutron stars and black holes there might be in the universe, because we know that there are lots of supernova in the universe. that explosion, if it's not perfectly symmetrical, if it's not perfectly spherical, will also produce gravitational waves. Those gravitational waves will be like blips, very difficult to detect, but still blips that we could detect in detectors like our LIGO detectors I'll tell you about. Those neutron stars that are left by the supernova are actually very, very interesting objects. They, first of all, have an electromagnetic beam, like a jet. It's not a jet that only happens once and goes away. It keeps moving around. It's actually the star rotates, but the axis of this beam is different than the axis of rotation, just like the north and south magnetic poles are different than the Earth's north and south geographic poles. So the same thing happens with a neutron star, which means that these radio beams, or mostly radio beams, pulsate if we are happy enough to be in the way to detect these radio beams. So sometimes we are looking at the neutron star from here, and we see a radio blip that comes periodically, every time that the beam points to us. And these radio blips are very, very, very precise. In fact, they are almost as precise, or sometimes more precise, than atomic clocks. We tend to think of stars as very messy systems. These are actually very, very precise systems. We can see these pulsars not only from the radio beams, we can also see sometimes the jets, sometimes we can see the nebula around, and that is because they happen with a supernova. This is an image of the Crab pulsar and nebula that was created by a supernova. Now, the fact that these neutron stars emit these radio beams that are so precise is something that we use also to detect gravitational waves. And I'll tell you more about that later. I'm building suspense here. So how many neutron stars are there in the universe? Well, we can try to estimate that from the number of supernova explosions that there are per galaxy. We also know how many pulsars there are. So we have observed about 2,000 pulsars in our galaxy. Most are radio pulsars, some are X-rays, some are gamma rays. But there are about 100 million neutron stars, perhaps 1 billion neutron stars in our galaxy. And the stars might produce gravitational waves of a constant frequency related to the rotational frequency of the star if they are not perfectly symmetric. Now, with the supernova explosion that I showed you, it's easy to think that it might not be perfectly spherical. And in fact, this sphericity is amazing. It's a part in 100, part in 1,000 for a supernova explosion. For these stars, they are the smoothest objects known in the universe. I told you that a neutron star of the mass of the sun would have the size of Manhattan. The mountain that you would expect on that neutron star of the size of Manhattan would be this high. So imagine a spherical object the size of Manhattan with this high of a mountain. That's how smooth neutron stars are. Nature is amazing. It never stops to amaze me. So they are very spherical, but not perfectly spherical. If they are not perfectly spherical, then theory predicts that they will emit gravitational waves. This would not be a rumble. This would not be a blip. This would be a constant sine wave in the universe, in this fabric of the space-time produced by the neutron star. So yet a different gravitational wave. Oh, by the way, in the previous one, if you look at Einstein at home, you can help us look for those sine waves in the universe. So write it up or Google it, einsteinathome.org. Now, these stars are often in binary systems. About 5% of all kinds of stars are not alone, they're in binary. So not every star finds a partner like most of us do, but only about 5%. So they're lonely objects. But still, I was telling you that there are 100 million neutron stars in the galaxy. 5% of those are a lot of those in binary systems. And in those binary systems, often both stars end up as neutron stars or a neutron star and black hole or two black holes. These binary systems, like I told you earlier, they would circle around each other. They would produce these gravitational waves that carry energy away. Because the system is getting closer and closer together, then the gravitational wave is going to have a higher and higher frequency, and it's going to get larger and larger because the stars are getting closer together. So the gravitational wave that we expect from these signals is not a constant sine wave. It's not a blip. It's a chirp. It's like birds singing, and I'm a very bad singer, so I won't try it. But it's like a bird that's singing with a higher frequency and amplitude. Whoop! See, I'm not very good at that. That's about as good as it gets. So those are the ones we want to detect. Those are our best target for ground-based interferometers, LIGO detectors that I work with. Now, this is also our best evidence that gravitational waves exist, because there's been at least two, and we hope there are more, systems, binary systems in our galaxy where we can see the radio blips from the stars, so we know how far apart they are, and we have seen them getting closer and closer together. The first binary system that was found by Hurls, by Taylor and his graduate student Hurls, working in Arecibo, with what I suspect was a very, very boring thesis. He had to measure very small disturbances in these radio blips to see whether they were due to a companion to the pulsar that was producing the blips. And he discovered, doing that very hard work, the first binary system, but when they kept watching the binary system, the stars kept getting closer and closer together, and you may not see the x-axis in here. The y-axis is the distance, something proportional to the distance between the stars. The x-axis is years, and this started in the 70s, and this is in the 2000s, so these are 30 years of data showing that these stars are getting closer together, just like the theory predicts, because the gravitational waves are carrying energy. So some people say that we have seen gravitational waves. We have certainly seen the effect of gravitational waves. And that was worth a Nobel Prize in '93 already. And actually, Hurls went on to work in industry and do other things, but Taylor still works looking for these stars and measuring distances between stars. He's amazing. So now I want to tell you about how to measure these gravitational waves. How do we detect them? I first need to tell you that they have not yet been detected. We have been looking for these waves for tens of years. The first detectors were built in the 60s. There were other kinds of trying to see distortions in space-time since the 60s. We have not yet detected gravitational waves. But I told you that they exist, so it's not that they don't exist. It's that the theory tells us that the disturbances in space-time are very, very, very small and very difficult to detect. How difficult to detect they are? Well, I told you the best target source we have are these binary systems getting closer together. The gravitational wave will be most powerful just before the merger. These mergers happen about once per 10,000 years in our galaxy. So that means that if we want to see one per year, we need to look at tens of thousands of galaxies, and we have not been able to do that. We have not had detectors as sensitive. Now that tells you the rate. Let me tell you about the amplitude. A binary system merging in the Virgo cluster, let's say, that's a cluster of galaxies where our Milky Way lives. And that happens once every 100 years or so. That merger would produce a change in distance near Earth that would take the Sun and the Earth apart by 1 atomic diameter. That's a part in 10 to the 21. So it would change the distance between you and me in a part in 10 to the 21. That's the calculation that made Einstein think that these gravitational waves were irrelevant. You could never measure them. He was wrong. We have not measured them yet, but we know there are many different ways of measuring them. I told you about many different sources of gravitational waves, from the early universe to supernova explosions to mergers of black holes and neutron stars. Those gravitational waves not only have different signatures, but they have also different frequencies. So here I have a plot of the amplitude of those gravitational waves. I told you that these binary neutron star mergers would produce a part in 10 to the 21 distortion in distances. That's about here. But there are these early universe gravitational waves at much, much lower frequencies would be much larger. But that doesn't mean they're easier to detect. We are trying to detect those early universe gravitational waves with the imprint in the polarization of the cosmic microwave background. That's what you heard. Those are the news you heard about BICEP. Again, those seem to have caused by dust, but there are lots of experiments trying to do the same, and it's just a matter of more sensitivity. That will come in a few years. I told you about pulsars being very precise clocks. You can use the radio beams coming so precisely from these neutron stars that are in different parts of the galaxy as ways of measuring the distance between the pulsar and the Earth. And if there is a gravitational wave going through the galaxy, it would change those the timing of those radio beams, and we would notice that. So that's called pulsar timing, and there are arrays of doing that. There's an array in North America, an array in Europe, an array in Australia, and they would be looking at the primordial background, but also at many, many of these mergers of black holes that would produce a rumble because they all mix together. I'll tell you more about ground-based interferometers. This is using an interferometer that is a laser beam going in two different ways and then using the measurement of the timing of the beam with respect to that one, measuring the interference in the way back, to measure distortions of the distance of this distance with respect to that distance. We have those detectors working at this precision at a few hundred hertz, and that would allow us to see these mergers of neutron stars and mergers of neutron stars and black holes, supernova explosions in our galaxy. The black holes in here are what we call small black holes that have a few times the mass of our sun to about a few hundred times the mass of our sun. But you probably all know that there are big, big black holes, especially at the center of the galaxies. We now believe that almost every galaxy, if not every galaxy, at the center has a big black hole. Our galaxy at the center of it we know, has a black hole of about 3 million solar masses. That's huge. And you know how we know about that? Using Newton's law. We use Newton's law to look at stars that are orbiting around that object at the center of the galaxy, and that's how we know the mass of that object at the center of the galaxy, and we know that it's about 3 million solar masses. We know that it's in this small space, so it's so compact, it has to be a black hole. We don't see the black hole, but we see what goes around it. We also know that galaxies merge. We have seen evidence of galaxies merging. We have caught one in the act of merging. Those mergers of galaxies are mergers of black holes, of binary systems of black holes. And those could be measured by a space interferometer, putting this kind of device in space. So you put free masses, satellites, And then you take a laser to measure the distance between those satellites, and that way you would measure the distortion in that distance produced by a gravitational wave. That's a project that's not flying. It's actually gone up and down from the books for a long time. We like to call it LISA. It's now being considered by the European Space Agency. So this tells you that there are lots of ways of looking for gravitational waves, and there are lots and lots of people doing it. And of course, there's a lot of money invested in this. Much of it, your money. This is your tax dollars at work. I think at good work. So how do we detect these gravitational waves with an interferometer? You might know that the interferometer that Michelson and Morley used to detect the velocity of ether that they didn't detect, and that's why we know that ether doesn't exist. So it all goes back to relativity experiments. What the interferometer does is use a beam splitter to split the laser in two paths and then use mirrors at the ends to measure the light coming back. And then when the light comes back, it splits again in two. So there's half a beam going there, half a beam going back. When this beam is coming back, there's half going back, half going here. So at the output, you can tell more or less light depending on whether these waves, this wave and that wave, are one on top of each other or one canceling the other. That's why we use interference to measure the difference in distance between this distance and that distance. And gravitational waves, if you do the math, have a character that's called quadrupolar, meaning that it changes distances in this funny way of making circles look like ellipses. It doesn't make circles larger and smaller. It doesn't change distances that way. It makes a circle convert into ellipse back and forth. And that's exactly what we would measure with an interferometer like this. Now, I told you that what we want to measure is a part in 10 to the 21, actually better than that, for this distance. So how long do we have to make this interferometer to make this effect measurable? Well, I told you that if we make the interferometer as big as the distance between the sun and the Earth, we can measure an atomic diameter. Atomic diameter is easy to measure, but not on that scale. We need to make it smaller. So we can put it in space. That's what I told you about LISA. Or we can put it on the ground. If we put it on the ground, then you have to talk about kilometer scale. And that's what we have with LIGO. LIGO is a US national project handled by Caltech and MIT that has built two observatories, one in Hanford, Washington, and another in Livingston, Louisiana, very close to where I live, so this is my favorite one. And you can go to Google Maps. These are actually Google Maps of those and see them. They are big enough to be seen in Google Maps. They are 4 kilometers long. Now, we don't use a metric system often enough. I think you all know how much 4 kilometers is, but it's more than a mile and a half. This is a huge distance. And even then, we have to achieve precisions of a part in 1,000 of a proton diameter. So here is when usually the question comes, you cannot measure a proton diameter, let alone a part in 1,000 of a proton diameter. So how you do that? Well, we use lots and lots of technology and tricks. One of those tricks to avoid measuring nuclear vibrations is to use laser beams. This laser hits the mirror and averages the position on the mirror. The mirror is this big, and the laser beam, when it gets to the mirror, is this big. So we are averaging the position of these many atoms on the front of the mirror. So we can do that. In fact, we have done that. We have operated these detectors with that precision, a part in 1,000 of proton diameters until 2010. And since 2010, we have built advanced LIGO detectors that are 10 times better. And we just finished installing those detectors this year. We actually had a dedication of those detectors in Hanford, Washington, a couple of weeks ago. And what's advanced about advanced LIGO? Well, these initial detectors I told you about, where we achieved this precision of a part in 1,000 of a proton diameter, would let us see coalescences of binary neutron stars in the Virgo cluster. But I told you those happen once every 50, 100 years. So we took data for a couple of years. We didn't see anything, but we weren't expecting to see anything. Actually, I was expecting that we were going to be lucky, but we had to be very lucky, and we weren't. But we kind of expected that. So we were already working. We had already been working for decades on technology to improve that initial reach. And these advanced LIGO detectors that, like I said, have been finished being installed, but they're not yet at the sensitivity we want, will be 10 times more sensitive. If they are 10 times more sensitive, then we see a volume that's 1,000 times larger. So we see 1,000 times more galaxies. We see 1,000 times more binaries coalescing. And once we reach that sensitivity, we expect to see tens of events per year, perhaps hundreds, perhaps a few. Actually, astronomers have their uncertainties in the order of magnitude. So it's very difficult to predict how many we will see. But once we begin seeing those, we will know what is the rate of these binary mergers. We will know how many binary systems, how many neutron stars, how many black holes are out there, what masses they have, how much they spin. We will know a lot more about that universe, and that's what's so exciting about this. Let me tell you that we'll have a short data-taking run later this year. These detectors are already at 3 times the sensitivity of initial LIGO. That is not yet enough to make us think that we could have a detection, but perhaps we'll be lucky. But then from this year on, we'll begin taking data once a year for a few months with better and better sensitivity until we get to these 10 times. And I think that before we get to that sensitivity, we'll see the first gravitational waves, and then the second, and then the third. So the future is very, very close and very exciting. Now, this technology is very complicated. And let me show you what we have in here. So the laser, it's a high-power laser. That's how we went from initial to advanced. It's using, one of the reasons we did, is using a much higher power laser. It's a very stabilized laser. You can see that these are crystals, so you need to wear bunny suits. It's actually not very comfortable to work in these environments because you have to be always so clean, so careful. The mirrors are not mirrors bolted to a table. They are 40-kilogram masses, crystals, also fused silica mirrors that are hanging from another mirror, that are hanging from blades, that are hanging from blades, that are hanging from an active seismic isolation system. And we need all of that to make sure that we don't confuse our gravitational waves with the ground, which is rumbling all the time and making our mirror move. So we isolate our mirror from the ground motion through all these pendulums. You may not know, but pendulums are very good seismic isolators, and that's why we use quadruple pendulums, but we also use ways to reduce seismic noise, measuring it and canceling it. We do all of that, the laser, bouncing back and forth from these mirrors, travel in vacuum tubes. Those 4-kilometer detectors I told you is the laser traveling in a beam tube that's about 1 meter in diameter, 4 kilometers long. And this is ultra-high vacuum. So this is the largest vacuum system in volume in the world. And there are 2 of those on top of that. And then there are lots of other auxiliary optics that we need to have to know what all the beams are and how they move, what they are doing. We have mirrors looking at the transmitted light. We have mirrors looking at the output of the interferometer and cleaning it with something that we call a mode cleaner. So the technology in here is amazing. And the engineering in here is amazing. We have not just physicists looking at the data and designing the interferometer, but we have optical engineers, electrical engineers, mechanical engineers, all talking to each other, putting all of this together. It's an amazing experiment. And of course, that's what I like the best about it. So what will we do with this? We will detect gravitational waves. What can we do with them? Well, of course, we will be very happy detecting these disturbances of dynamical space-time here in Earth. That, to me, is just mind-boggling. But that's not worth the hundreds of millions of dollars that we have spent in building these detectors. What is worth is that we are going to be doing astronomy that will tell us not only what are black holes and neutron stars and unknown things and supernovas out there in the universe, in our galaxy and other galaxies, but we will also be able to learn from this by putting together the information we get from the electromagnetic spectrum that we receive from these systems and the gravitational waves, which have never been seen before. It's in putting these things together how we learn about the universe. And you might have seen this is one of my favorite NASA pictures. It's very old, but it's still one of my favorites. This is what our Milky Way looks like. This is more or less what you would look like in a very, very dark night. Actually, the best way to see the Milky Way is from the southern hemisphere. That's one of the things I miss. I am from Argentina, and I have to say the night sky from Argentina is a lot nicer than from Louisiana now. Of course, it's difficult to see it if you are in a bright city. But anyway, that's what you would see in the optical spectrum. But if you look at gamma rays or X-rays or infrared or atomic lines, it's very different. And that's how we know what is happening where at what energies and what is changing. Some of these features are changing, some are constant in time, some are blipping, some are not. That is how we do astronomy today, is using many different windows. Gravitational waves will be a new window to the universe. So we have an event here, that's an astrophysical event, and we want to see gamma rays, neutrinos, gravitational waves, cosmic rays, X-rays. We want to see all of these different windows to the same event using different instruments. That is what's being called multi-messenger astronomy, even without LIGO, because you can see things in X-rays and gamma rays and so on. But now with gravitational waves, we'll be seeing a completely different universe there. Gamma ray bursts are the main example of these things. You might have heard about gamma ray bursts. They were first detected by military satellites that they weren't looking for that, but they found these blips in the gamma ray spectrum when they were looking for nuclear explosions. It turns out that they knew these weren't nuclear explosions. They couldn't tell other people what they were doing, but they finally did. And then there were other experiments our satellites built to look for these gamma rays. They found them. They came from all over the sky. They come in two kinds, short and long. Shorter than 2 seconds, longer than 2 seconds. And we think now, we have theories, although not quite proven yet, that the long gamma ray bursts happen when we have supernova explosions, these core collapse supernova I was telling you, that end up producing a compact object like a neutron star with a jet, and that explosion is what produces the gamma ray burst that we see. And that's longish. It's longer than 2 seconds, sometimes 10 seconds long. But there are shorter ones, and those shorter ones we think are produced by the merger of binary systems in which one or both of the stars are neutron stars. If they are both black holes, they don't have matter enough electrons to produce gamma rays. So one or both of these stars have to be a neutron star. But when they merge, they have this explosion when they produce the black hole at the end, and they always produce a black hole at the end. And that, again, that would emit gamma rays, which is what we see. So these gamma ray bursts, the name tells you that they are best detected in the gamma ray spectrum. But we see them, now that we have been looking at these for a long time, we see them in many different wavelengths, whether they are produced by a binary merger or by a core collapse supernova. They end up with a black hole with an accretion disk, or a magnetar, which is a neutron star with a very, very high magnetic field. And then we see not only the gamma rays, which are the prompt emission, at the same time that we would see gravitational waves, but we also see an afterglow that is seen in the optical, in the X-ray, in the radio, in the optical spectrum within hours, in the X-ray within days, in the radio within months. So these are all the different electromagnetic windows to that event. If we have gravitational waves, we would be able to measure the amount of mass in this system, the spin of the system, the macroscopic quantities of the system that we cannot tell from all of these electromagnetic signals. So this is what we call multi-messenger astronomy. Now, to do this, you not only need to detect gravitational waves. You need to know that those gravitational waves are coming from the same event that's producing the gamma rays or the electromagnetic waves. How do you know where a gravitational wave is coming from? Well, that is more difficult than you think. If you think about LIGO as a telescope, then you might imagine that the telescope is looking at some direction in the sky. That is not the case. LIGO as an interferometer is more like a microphone. It can measure gravitational waves that are coming almost from anywhere. There are only a few directions where a gravitational wave can come from that would not produce a signal. But from most directions, it would produce a signal with different amplitudes. What that means is that if you detect a signal in the detector, you don't know where it's coming from. So what do you do when you want to have good sound? You have more microphones. You do stereo. That's what we do. So we have 2 detectors in the US. That's not quite enough. But we collaborate with another detector in Italy. And with 3, we can do triangulation. So we know that these gravitational waves travel at the speed of light. Well, that's a theory. But once we detect them, we can test that. But because they travel at a finite velocity, then there will be a timing difference, a difference in the time of arrival of these waves. And from that time difference, we can tell where the gravitational wave is coming from. Now, the localization we would have is quite poor, at least for astronomical standards. But the idea is that once we know more or less the region it comes from, then we look in that region with satellites in X-ray, gamma ray, with telescopes in Earth, like LSST, which is a big survey telescope that's being built. And then we find coincidences. Now, that sounds more difficult than, it sounds easier than it sounds. It's actually a difficult problem that we are working on, but we are getting ready to do it. Now, I told you that we have a network of 3 detectors. Those are the 2 advanced LIGO detectors in the US and advanced Virgo in Europe. We also have a 4th detector in Germany that's called GO600. That is part of the LIGO collaboration. However, that one is 600 meters long, so it doesn't have as much sensitivity. It's not competitive to this. It is the one where we develop a lot of the technology that then we use in advanced LIGO detector. And more importantly, is the only one that's running now when the other advanced detectors are getting prepared to run later. So if there's a supernova in the galaxy, we don't want to be all off at the same time. GEO is in what we call astro watch time, keeping watch in case there's a supernova. But those are not the only three. There's a detector being installed in Kagra. That's an underground cryogenic detector in the Kamioka mine, where the super K detector is there looking for neutrinos. And we are also, there used to be two LIGO detectors, two initial LIGO detectors in the Hanford Observatory. We were planning to have two advanced LIGO detectors in Hanford, but like I told you, for triangulation, it's better if we have it somewhere else. So India is preparing to build an observatory to host this third detector. And with that, we can get a lot better localization. If we have three detectors, the two LIGO detectors and Virgo, and we want to know how a signal is localized, we know that if it is coming from this direction, the actual signal is coming from this direction, the uncertainty is very, very big. If it's coming from this direction, it's kind of small in this scale, but it's huge for astronomical standards. It's tens of square degrees. And we have some blind spots. There are some directions from which we wouldn't see gravitational waves. If we have 4 detectors, if we have this LIGO India detector, these uncertainty ellipses become a lot smaller. That means our localization becomes smaller, and there are no more blind spots, no more red crosses in there. So that's where we want to go. And that's where I end my talk. Thank you.